This video is going to talk about resonant column length and the speed of sound, and so some of those concepts are a little bit odd because we don't really know what resonance means in terms of sound columns, but we're going to talk about that today. So there's a couple of pointers that we should probably look at beforehand. Now, some of this has been pre-drawn and we can make this available for you online, so don't worry too much about copying this. First of all, we have to remember the concept of transverse waves. So I've drawn a transverse wave here, and it's similar to what you see with water, right? Water waves kind of look like that. But let's remember that a transverse wave propagates this way while the particles are going up and down. So we say the particle motion is vertical or perpendicular rather to the propagation. So propagation is the way it goes, but then the particles are actually only moving up and down. Particles don't move with the wave. And with a transverse wave, if we go from one point on the wave to the subsequent identical point, then that's how we do a wavelength. So it doesn't have to be peak to peak. It could be this random spot here until we find the next one that is identical to it. Okay, we use the Greek letter lambda because the letter L we're going to see is actually for sound length, kind of. So here we go with sound waves. You see, sound waves don't travel and aren't described as transverse waves, but they're more like longitudinal or compressional waves. So a compressional wave, though, if you look, this segment here called a compression is not the same length as this rarefaction here. This segment here is a different length, okay, than the compression part. But together, they combine when you go from the start of a coil, a compression here, to the start of the next one, then that's the wavelength. So there's some comparison there. We shouldn't worry about that. A rarefaction is a place where there's open coils, and then this is the compression, which makes sense. There's an old phrase called rarefied air, and that means the room got quiet. So, excuse me, when you talk about rarefied air, you're talking about where there's nothing in the air. In space, they talk about outer space has rarefied air, so there's not much stuff there. Okay, so why do we do this? Why are we going back to transverse and longitudinal waves? Because although sound waves are compressional waves, it's much easier to describe them as transverse waves. So what we're going to do first is talk about how transverse waves behave, although compressional waves, they do the same thing. And that's how we're going to tie this all together. So here's a rope, and it's attached to a rigid barrier. Okay, a block of wood with a hook on the end. And as characteristic of waves, when this wavelet, right, a little wave pulse comes down, it travels to the barrier. When it strikes the barrier, however, it returns inverted. It flips. Okay, so we could say this is a plus magnitude and this is a minus magnitude. Excuse me. When they join together, if they are in the same place at the same time, remember this guy's going that way, this guy reflected. This is the first wave actually. He went through, bounced back. When they come to the same place at the same time, if the plus is +3 and this is a -3, they cancel out. And they simply travel through each other as though nothing happened, and so this red one will eventually be down here, and the blue one will be this way, and so on. Okay? When they combine in a way that cancels each other out, it's called destructive interference. Now, we don't have to totally cancel out, but this is the simplest example that if they do combine in the same place at the same time, then it's called destructive interference. So, of course, you're probably ready to learn constructive interference. So if we send a pulse through this rope, strikes the barrier. Actually, this red one would have been first, right? So we send him through, bounces back. Here he is. He's number 1. He came first. And then you send a second pulse, this guy here. If they should meet in the middle at the same place at the same time, much like their friends up here did, right? This time you don't get destruction, but you get construction. So it's the algebraic sum, actually. It's the algebraic sum of those two wave pulses. And then that's called constructive interference. So constructive in the sense that they grow or build. Interference means that they are combining or mixing together at the same time. But there's something that's important to remember, and that is this guy right here. So when you have a standing wave, right, you can imagine that you wiggle a rope or a string or something, maybe a metal compressed spring. You cause this vibration here. Let's start with blue. You send some wave pulses. Maybe you send several wave pulses, right? You're vibrating your arm up and down, and you send them through, and then they strike this barrier. But the nature of a rigid barrier is that you have to have what is called a node. You have to have a position of no motion, and it's bolted there for all intents and purposes. We could put a vise there, but the way this works is that it only causes a vibration through a node here. So this up antinode, that's what that is. Excuse me, an antinode is an up part of the wave, which, by the way, is also the amplitude, the maximum displacement from the origin. And this origin isn't really here. It's a reference line. It's not the wave. That's what the medium would look like if we didn't cause any vibration. But we can still use it as a reference, so we call it the origin. And so what happens? You propagate a wave, couple waves, right? Each time they strike, this up wave, antinode, becomes a node, and then it reflects inverted. We've seen that before. And so you could get a situation where the out wave and the return wave set it up like this. So you get an up and a down. And that's another example of how transverse waves work, right? Same medium, so you get this up and down business. We also have that with a compressional wave. We could talk about antinodes and nodes. We're not going to worry about that too much here, but there is a place where there's maximum motion and there's little motion, okay? Or pressure. It's really about pressure when we talk about sound waves. So let's look a little more closely, though, at what we're going to do with sound waves, because this really is a pre-lab. And if you have a rope, right, that nicely drawn transverse wave and a rigid barrier here, let's see what the analogy is when we transfer that transverse wave to the idea of a compressional wave, right, or a sound wave here. All right. So the way it works in lab is that you have this very tall graduate cylinder on the order of 2,000 mLs, and then you have this smaller diameter tube that fits into it. So this is water down here. And you tap a tuning fork, and it sends down its little sound waves, right? It's compressing the air, so jiggle, 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 all these compressions, and down they go. Now, they're supposed to be inside the tube, but let's draw them on the outside. And down they go. This is a rigid barrier for water, or for a sound wave, rather. So that water acts as a rigid barrier. And then, remember, if this is an antinode or a node, right, this has to be a node here, but it comes back inverted. Okay, so I'm not going to worry too much about compressions and rarefactions. We don't really need to know that right now, but when it comes back, and if this is a standing wave, right, this continues to vibrate. If we get a situation here where there's an antinode and a node, it's kind of like that up and down wave experiencing destructive interference. And we're not going to hear any sound. So we have a tuning fork vibrating at 440 vibrations every second, incredibly fast, goes down. But we can get a situation where, right at this opening, that we hear this loud sound. Okay, so we're going to talk about how does that work. All right, what if we have a situation where we send the wave down, we put the tuning fork above this tube, right? So now we're not going to show the graduate cylinder on the outside. This is the inside resonance tube where things resonate, where they have sympathetic vibration. A tuning fork is held above this, right? He's making sound. And let's say that there's a node here. Let's just say there is. Goes through this tube. Again, it's going to be compressional wave and rarefaction, but this works better. Goes through. There's another node. There's an antinode. There's a node. So if this were a string, this would have to be a node here, and the water acts as a rigid barrier. Then it reflects on the other side, right? It gets inverted. So if this is up, this is down, right? It comes back. In fact, we could do this, right? We could just turn it sideways. And what happens? You have a node, antinode, and so on. Hits this vise or this barrier, in this case water, bounces back upright and returns. Okay? But if these two here, this is a node and this is a node, if they are at the same place at the same time, we don't notice it in lab. We don't have any sound difference. We don't hear any loudness. Okay? But there are times when we do this situation and we actually do hear some sound. Let's look at that situation here. Now we could set it up so we tap a tuning fork, and now we have an antinode here. Okay? What's it do? Travels through. There's the first node. There's an antinode. As required by a rigid barrier, there has to be a node here for reflection. It reflects opposite or upright or down or flipped, however you want to do it. If this is the incoming, then this is the outgoing. There's a node there. But now, remember, we started with an antinode here. Maximum displacement from that origin, which I drew in. You're welcome. This antinode is matching with another antinode, and it actually gets twice as loud, right? If you had two, here's an antinode, here's an antinode, same size, then it's the algebraic sum. Now, some of you might be saying, well, wait a minute. This is an up, and this is a down, or this is a down, and this is an up. That's not how it works with compressional waves, right? So this would probably be, you could draw this as your compression. And this is another compression. But they're compressions. Okay, so they both count as both up or both down. They're adding the size together. So what do we have here? In this case, we can arrange the length of this inside tube. Right, here's your graduate. We can arrange this so that inside tube above the water causes an antinode, and you hear a howling sound. And you'll see that on the YouTube video. It actually works. We used a tone generator and a phone. Okay, so resonance is also known as sympathetic vibration. Now, what does that mean? Sympathetic, to join, to be the same, to agree, right? To accompany. And so if you've ever been in a car, for example, and your buddy plays the music too loud, you can see the rear view mirror actually vibrating. Okay, that's because the sound is so strong that it's causing vibration. It matches your rear view mirror and it causes vibration. That's also true with the vibration of the windows at your house. If your friend pulls up to the house and it's so loud, not every sound causes those windows to vibrate, but some of those frequencies do. That's called resonance or sympathetic vibration. Okay, so what do we see here? This business of closed tube resonance. Okay, let's figure that out. Let's zone in on this guy a little closer. All right. So what are we talking about? In lab, we have closed tube resonance. It's closed because the end here is a water boundary. So sound waves are not going to transfer from air into water. If you've ever been in the pool, people screaming, as soon as you go underwater, you don't hear them. That's basically what's going on here, okay? But what happens here? If we look at this incoming wave, right? Here's a node, so that's halfway through the wave. Here's the second half of the wave. So we don't even have the entire wave drawn in here yet. We don't need the whole wave. But what happens here? This is a quarter wavelength from the barrier to there. And then there's another quarter here, and then a third quarter, and then a fourth quarter. Now, mathematicians are probably tempted to call this half. Don't do that. Okay, don't do that here. Do it somewhere else. Because when you're dealing with closed barriers, or closed tubes rather, everything's in terms of quarter lengths. 3/4 length, there's 5/4, 7/4. Okay? So be discouraged to do that. Don't call that half, and don't call this 1. Call it 4/4. Okay? So what happens is, if we look at this situation, we get a howling sound here, because these two antinodes are very strong. They reinforce each other, and that happens when we have 3/4 of a length. But we could change the length of our tube here. What if we just said this was the opening of our tube? Right? Well, that's when two nodes come together. That doesn't make any howling sound. But if we could, there's another opening of our tube, right? If we had the tuning fork here, started with an antinode, right? Goes down, reflects inverted, comes right back. So the minimal portion of a wave that does that vibration stuff that makes it howl is a quarter length. And then it happens at 3/4 lengths. And the rule is that it happens at what we call odd quarter intervals. So if you have a closed tube and it starts to howl, it's going to be at what we call odd quarter intervals. 3, 5, 7, and so on. Okay, so that's basically what that looks like. Here's where it gets interesting. If we go back to this column here, I'm going to go back to that column here. Wherever we had a howling sound, right, we're going to call that L here. Okay? That inside tube above the water to the top of the tube. But see, we want the first time it howls. So technically, we want this length here. That is what we call the resonant length. Okay? This guy has another term. He's basically a harmonic. Right? This whole long one is the second time that happens. It's a multiple. Okay? So we don't really want this guy. We want this first one. That first column. Okay? And when we do this wavelength business, I want you to see right there that that's what we talked about. When we are in lab and you measure that, you think mathematically, okay, if I knew that everything is a quarter length, right? This L represents 1/4 of that sound wave. If I multiply it by 4, I should know the length of that sound wave. Yep, sounds good. However, we have to account for something. It turns out that the diameter of the tube that we use, the bigger it is, the more effect it has on the actual wavelength. So if you actually just took and you did your lab and you said, oh, I multiplied that length by 4, you'd find out, oh, my wavelength isn't quite right. Well, what they found out was the diameter, inside diameter of that tube that we used, you have to multiply it by 0.4. If you add that, then multiply by 4, you'll get your correct wavelength. So, experimentally, it worked out pretty well. L is the resonant length. D is the diameter, inside diameter of the tube, using calipers if you can. All right. So let's look at this business here, because you'll also need this for our lab. The speed of sound at 0 is 345 meters per second. Okay? But as the air gets warmer, the sound can travel faster. The particles are moving faster, right? Because when things get warmer, they vibrate more frequently. So for whatever reason, then sound travels faster in warmer air. And we actually know that for every degree above 0, it gets 0.59 meters per second faster. Okay, so how do you do that? Well, if it was 0, then you'd have 0 times 0.59, and that's obviously going to be 331. Okay? But you could do it for something as simple as 10 degrees. Let's do that here. Right? So 10 degrees is pretty cold water. You're not going to do a lab probably with 10 degree water. But if you did, right, this comes 5.9. You add that, it's like 337.35 or something like that, right? Okay, that's what I'm going to call it because I don't have my calculator and I'm not wasting your time. All right, so where does that get us? It tells us that if we know the resonant length of a sound wave, then we can say, oh, we think we know how long that sound wave is. And then we can figure out velocity, and I'll show you that in a minute. But there's another situation here. Okay? It turns out that there's such a thing as open tube resonance. In other words, you can get the howling sound with an open tube rather than a big old tube with water in the end. And how does that work? Well, you can see it through the paper. Okay? This time, we have to remember this should be open, and it's probably drawn wrong, but we could, yeah, I'm not going to, let's do that. Maybe that'll help make it look a little better. Okay? And so now, for whatever it's worth, this is a sleeve on the inside of a bigger tube. And so we just adjust this back and forth. And if things work out right, we get howling. But we get howling for a different reason. Okay? Here's the difference. This opened area here isn't like the block of wood. It's not like the water surface. This is not rigid. This is more like a situation where you have a rope and there's a loop here. Like this should have been drawn as a hoop, right? So there's a little hoop here, and it's free to move, right? It's free to move there. Okay, so we'll just kind of draw something like that. And so when this wave pulse comes in, it hits this, but instead of being inverted, it actually goes upright and it returns the way it came. In other words, if it was down here, hits that ring, it's going to return on the down on its way back. Okay, so that's an antinode. Antinode on the way in, antinode on the way out, still a node, right? Antinode here, antinode way back. So there is a difference when you have an open tube. So if we do like we did with the quarter lengths, this time it's a little different. Okay? We have a situation here. This is an antinode. Okay? Let's just take this rope and put a graduate cylinder around it, or a resonance tube. Okay? What'll happen? We get howling at this situation right here, right? Because the incoming is a antinode, it returns, it's an antinode. Okay, you get howling. Okay? You don't get anything here, right? Because two nodes will not combine to make it louder. In fact, there's nothing there. That's why it means node motion. But here, you'll also get sound. Okay? Well, look at what this is from here to here. That's an entire wavelength. Okay? What we do is when we talk about open tubes, right? When we talk about an open tube situation, we use half intervals. So these two intervals here. So we would actually, if we had the tube, it would be here, and then we'd hear the sound. Okay? So what we do is for open tubes is we use what are called even integer half lengths, right? So half lambda, full lambda, 3/2 lambda, and so on. That one they do actually consolidate. All right, so let's do one more thing before we wrap this up. The intention of the lab is that we're supposed to determine the speed of sound by using the resonant length. Okay? So let's say that we have a situation, we said L equals 34.3 centimeters. Okay, and we use this in a closed tube situation. Then we know that lambda isn't just 4L, right? We know that we actually have to make some accommodations for the diameter of the tube. So the resonant sound length, where it howled, was actually this situation. So it's basically 4 times 34.3, but don't forget your diameter here. Be careful to make sure that your centimeters and meters are correct. Okay, so now we have this wavelength experimental. Okay, we also have the frequency that caused that. And it might be something like, I don't know, let's just go with 408 hertz. Okay, it's probably an odd number for a tuning fork, but we could use a sound generator. So now we have a frequency, right, which is new, and we could use F. Either way, both of those are the same. So what are we supposed to do? We have V equals F lambda. The velocity of sound is equal to the frequency times lambda. So how's this work? Well, this came from the tuning fork, and we will tell you that information, or it may come from a tone generator. Okay, but that's the frequency in hertz, so it might be like concert A, 440 hertz. You might see something like this, 520 VPS, vibrations per second. Okay, same thing. Same thing. This came from the equation that we just looked at. Lambda, resonant length, I guess you could say, comes from 4L plus 0.4D. Okay? You use these and you come up with the speed of sound. Let's say that it becomes 348.7 meters per second. You say that's what we did experimentally. That is our experimental, we tested it. Okay? Well, we actually have a way of knowing if you are correct, and that is this equation that we talked about before. The speed of sound is accepted to be 331.45 plus this meters per second per degree Celsius times T, right? And so if you do that for whatever your temperature is, let's say that you come up with 346.6 meters per second. Okay, this is your accepted. There you go. That's all you have to do is basically compare the experimental with accepted up here, and you could do that in terms of a percent error or something like that. So let's walk through this one more time just to make sure you get it, and then we'll let you go. All right. So you have the resonance and speed of sound. The idea is that when a sound wave is described, we don't really use transverse waves because sound is not a transverse wave. But it turns out that it works out much better when we're drawing these out. So there's a compressional wave here and a rarefaction, right? This is actually how sound works. It's like a slinky, right? But the transverse waves are much easier to explain the concept of reflection and reinforcement. A little pulse here strikes a barrier and it comes back upside down or inverted. That happens when the barrier is rigid. Okay. If they should meet together at the same place here, a plus and a minus would cancel out. But two pluses, if they came back together, right, they would construct, they would build, they would grow. And so that's called constructive interference. We also have to talk about the concept of a standing wave, and that's what this is, where we have a rope that you're going to jiggle up and down with a rigid barrier. There has to be a node here, however. That bolt or that clamp is going to hold that in place. Again, that wave inverts on the way back down. You could set it up so that you get a standing wave, and so this situation here where the nodes meet, right, and all we're really doing is moving the wave particles up and down. We could also talk about that with compressional waves. What we have here, though, is another example of a transverse wave. And we're going to talk about how now a tuning fork causes these compressions, right? So they're actually squishing, coming back up. It's actually happening inside that tube, okay? But what happens is something unique, and that is if we set it up, we can actually have an antinode, a maximum displacement from this origin here, this reference line. It goes down, comes back. It has to be a node, comes back. If you get two antinodes at the same place, they actually reinforce. Compressional waves, they get louder, okay? And so we will hear that in lab. We can measure that length. And the first time you'll get that is at the first quarter length of the wavelength. It doesn't happen at the second quarter, but it does happen at the third quarter, okay? So we have rules for that. And that says those lengths, where it howls, happen at 1/4 intervals of the wavelength if the tube was closed, okay? So that equation says you can now know the wavelength. It's basically 4L, right? 4 times L. But because the diameter has an effect on the length of that column, we use this situation, okay? So just make sure that you're doing that. L should be the first time you hear the sound. There are multiples of this, so be careful, okay? Now, there's an accepted way of calculating the speed of sound, and if we do this, we know that as air gets warmer, we can add something based on the temperature, so we could actually have the letter T in there. All right, so here's an example of a calculation if the air is 10 degrees, okay? There's also this concept of open tube resonance, and that means that the wave that comes through here will actually return when it's, if we drew this as our origin, right? That this needs an opened end, right? And so now we have a situation where there's an antinode here, and that pressure will bounce back off of the air on the open end of the tube, and then it comes back. We have the same situation as we did with closed tube, but this time it's a little easier. Wherever there's an antinode on the way in, it's going to be an antinode on the way back. Boom. That happens at half-length intervals. Finally, how do you calculate the speed of sound based on a tuning fork that makes a column of air howl? That's really what this bizarre lab is about. You measure the length where it howls. If it's a closed tube, you do this. Multiply by 4, but before you do that, add this factor, then multiply by 4. That's your experimental. You're saying, I believe that the length of the sound is this. Okay? You'll have a tuning fork or a tone generator that will tell you this is the frequency. Those two things can be used to calculate the speed of sound. Tuning fork, experimental wavelength. When you multiply those together, let's say that you got 348. Okay? The accepted way to calculate sound is this method here. We've already seen that, so that's not a big deal. Let's say it came out to be 346. Then all you would have to do is compare 346 to 348 and call it a percent error. So that's how you do the resonant length of a sound column.